I'm going to talk about event source business applications. And business applications can be a curious topic to be excited about, for sure, but it's kind of been my passion for a while. So we're going to do a quick alignment on what they are, my take on the very broad status quo, which is not going to be what most folks in this conference are doing, but much more in the broader world. And then kind of a deep dive into how we approached getting to doing an event source application and kind of the process of starting to evangelize that internally and build that inside of our ecosystem. My name is Peter Royal. I've been a professional developer for the past 2+ decades. Most of that has been doing business applications of some sort. And recently, that has been building tools to help power Netflix's studio and content production side of the business. So when I think of a business application, what's in my mind is a tool that is very tailored to a specific domain and very much in a domain-driven design type approach. These tools are often custom tools that are developed for the specific needs that that business has, often for a specific area of the business. The usage is generally mandatory by the business users because the fact that the data is captured inside of the system is considered to be a strategic value for the business. So we want to put the information inside of the system so it is all in one place, and the business can then use the information therein to make decisions and continue with its operation. The application itself is a source of truth for what the domain is, and often what I like to consider medium-sized data. It's not the type of thing that you're going to need a super large S3 based data lake, data warehouse type approach for. But maybe it's a database server or two, depending upon the size that you have going on. And the criticality is much more the business importance rather than the raw request per second the service might be seeing. The data that's therein, if this is financial data, it's going to be very important that it is available and correct. And if people are doing end of the month book closing, that everything is there at the time that the business needs it, rather than necessarily some sort of continuous availability. It's the type of system that, yeah, if you took it down over the weekend, maybe that's okay because the business doesn't actually need it then. So my broad perspective on the status quo of many of these types of business applications, and this is very biased from my opinions and observations, but I hope that some of this will resonate with what you've observed as well. So many applications have now moved towards web-based UIs, maybe even single-page applications. In days gone past, this is the type of application that maybe was a Microsoft Access database. If you go back far enough, maybe Visual Basic applications when people were doing desktop applications. But as web technology has matured, the fact that you can now deliver an application with a browser has become very easy, and it removes a lot of deployment constraints. So things have been moving towards these web-based UIs. The way that the UI and the backend communicate is what I like to call REST in quotes, because this is not what Roy Fielding meant when he originally coined the term. It usually just means some sort of often underspecified JSON payload delivered over HTTP. Maybe there's some of the verbs that are used to indicate whether or not something is being created or deleted, but it's a very loose API. The underlying data store is probably a relational database, often MySQL, Postgres, Oracle, and it's often accessed via an object relational mapper. If you're in Ruby, it'd be like Ruby on Rails. If it's on JVM, it's probably Hibernate. The reasonability of the schema is going to depend upon how old the system is. A system that has been in production for 5-10 years often accumulates a lot of cruft where people are willing to add things to the schema, but the maintenance and removal of data is taken a lot more judiciously because you're deleting things. And the system is often, again, mutate in place where you're adding and deleting rows from the database, and the past data is gone. Often the business, unless the business had a very specific business need for keeping what the history was, this is the type of thing that application developers often let go and don't worry about. So the way that user interfaces have been happening has been changing over the past 20 years, and especially it's been in the mid 2000s or so. This, before, software was done mainly for people that needed software. When the iPhone really came out is when apps, in my mind, were really pushed forth to the broader world where all of a sudden everybody is using applications. And this really made this change in nomenclature also led to a change in the approach where now there's a lot more UX design being done on a much larger scale because for applications that are being pushed out to the world, having good UX is now a competitive advantage. And there's been a lot of changes from the web side for um, both on the web and apps that have changed the way interfaces operate that haven't necessarily percolated down to non-consumer based applications. And I've seen this manifest in the way that people think about the applications that they're using. So if you think about like from a browser and UX innovation, we have, first class streaming data now. Your app on your phone, it's updating live, it's keeping things, you can always see what the latest stuff is. We now have facilities for running things in the background. The technologies that are being used to implement this are being pushed more on the, like, let's call it like the consumer UI side. That is where GraphQL came from, and React, both coming out of Facebook. The idea of this, like the pull to refresh, or maybe not even needing to refresh, where your view is always live, is a thing in the applications that you use in your personal life. And you have, you have infinite scrolling, you have notifications, and a lot of things to kind of keep you in the loop as far as what that tool is doing for you. But this isn't stuff that's necessarily happening inside of business applications. It's a tool, business applications being a tool that is done that somebody has to use at work. These type of affordances aren't thought of, and some of them, especially the streaming data and the needing to refresh, I'm seeing disappear from the minds of product managers because it's now so commonplace elsewhere. It's becoming table stakes almost in what the system should do. And the way that applications have been built haven't been geared towards providing these sorts of features, which leads to this impedance mismatch in what the system that exists is capable of and what the overall capabilities of the system towards the users is desired. There's another big change that's happened, which is the cloud. Application delivery was previously, you had your data center and you deployed your application, and that was that. Now we're deploying into these virtual environments where even if you aren't using a public cloud, you are likely deploying into some sort of virtualized environment. And this has kind of affected system design because all of a sudden the reliability of the systems that you have has shifted. You now need a system that is reliable even in the face of more likely hardware failure because you don't have that same confidence that you have in that, that blessed metal server that might be sitting in your server room or your own data center. And one big change that has come out of this is this idea of reactive systems. And these are some ideas that, folks have put together regarding system building. And to give a little background about reactive systems, if you're not familiar, you've likely used one without using it, and that's a spreadsheet, which is when you change a cell in the spreadsheet, everything else reacts to it. And the system is, you know, the system is a projection of these types of concepts at a wider scale. There's two broad paradigms in programming. You have your imperative programming, where you're kind of writing an expression as far as what the language is telling you. You're writing in the code what's going to happen. And the declarative is the opposite, where you're expressing what you want to occur out of the system. And when you think about reactive programming and reactive systems, you're kind of inverting that, where you want to think about the data flows that are going to occur. And this is, thinking about, real-time systems, it's related to that. And the visual in my mind is plumbing, not necessarily the type you would find in the real world, but kind of that game genre where you have to link the pipes together in order to get things to flow. And this metaphor kind of carries over to the expression of a program. The faucets are the inputs and are the requests that your program receives. The drain is the output, and that's kind of the responses that your system is generating. And that's not just the responses to the specific request the system received, but also things like log statements and metrics. Those are kind of ancillary flows that are coming out of your application. And reactive programming is kind of the expression of your problem in that form, where you think about your program itself as inputs and outputs that you're connecting, and then your data is flowing, which for events is kind of what's flowing through those pipes are events relating to event sourcing, which we're all here because we're interested in that. And you can then take this paradigm from a process level and also lift it up to the system level, where it's not only do I have a process that is having these conceptual pipes inside, it is now a system that is composed of these pipes across multiple processes. And all this to lead to the reactive manifesto was this document written about how to think about your system in those facets, and a kind of a aggregation of architectural practices that were centered around this. And there's 4 principles that it has, and I'm going to kind of walk through each one in turn and kind of talk about how it relates to business applications and the value for that, and which then leads me on my path towards speaking about event sourcing. So the first one is responsive, which is, you want a responsive system. And from a business application, this is important because, for employees that are using a system, to a degree, time is money. And on the extreme end of the spectrum, it can kind of be the difference between life and death. There's an anecdote I had read on Twitter about somebody working in a hospital speaking about how slow loading images on radiology machines was a material part of the speed by which they could triage patients. And the lack of responsiveness in the system was an impediment towards their actual delivering of care. And that might not be, well, an extreme example. It's the thinking of system performance in that way that I feel is important. Like if you've ever been on the phone with somebody and they're apologizing for how their computer is slow when you're calling into a call center, you've experienced this, and it's kind of this like latent drag across everything that is not always appreciated. I think it's vastly underappreciated in business applications. The next one is thinking about resiliency, where failure is going to happen. Like, because as we've moved to these more virtualized environments, things fail. And if you don't deal with it gracefully, it's probably not going to happen gracefully. And for our business applications, the scope of the failure might be more controlled. You might think, I don't need to worry about resiliency as much because we only have a few things and we kind of take care of it. But this also relates to kind of like self-inflicted downtime, which I don't think people consider about as much. The big one being deployments. Whenever you deploy your system, how is that akin to the system crashing on a very temporary way? So if you can think about baking resiliency into your system, you're starting to set yourself up for actually continually deploying your code into production. And there's been studies that have basically said the more rapidly you can deploy your changes into production without failure is a metric that can be used to gauge a high performance team. So, and if you don't think, you need to think about the fact that a deployment is always putting you in a temporary unusual state. If you have whenever you deploy, you're either taking the entire system down for some period of time, even if it's very brief, where you now have no code running, or you have 2 processes running at the same time while you transition from the old code to the new code. And the more that you do this and get used to this kind of unusual state, the easier it's going to be for you. Elasticity is, another one of their principles that is useful, but not as useful for business applications. I think of it mainly as with cost management, and not something that is really not as important because our systems are more requests per minute, not requests per second. You don't have that same scale burst that you need to go. But it can help from a business perspective. You now maybe no longer need to over provision if you have expected spikes in load. Elasticity is the principle that I think is the least important for business applications. Message driven, and when thinking about system architecture and how I wanted to make a resilient system in a cloud environment, message driven is the one that really spoke to me. And because events are messages, and this is how these principles really align with event sourcing. The prior properties can be viewed as operational properties, whereas message-driven really fundamentally affects your architecture because you're now sending discrete messages around. When I mentioned the pipe metaphor, pipes don't necessarily contain a continuous stream. It's actually atomized into discrete messages. And your system is actually already composed of messages because that's how you receive your inputs. Ultimately, you're connected via TCP somewhere, and that's a packet switch network that is sending messages around. And we have abstractions that sometimes decompose that into something else to make it seem like a continuous change, or we lose the fact that those messages exist. But by keeping the messages and events as deeply into the application code as possible, becomes a very powerful primitive. So kind of taking the prior bits that I've said, thinking about both these properties about a reactive system, what is a business application, and how the application landscape itself has changed. I was thinking about how I wanted to think about forward-looking business application designs, and there are two broad constraints that I wanted to work with. The first is that I wanted to expose the system via GraphQL, and this is because of a larger strategic decision we have undertaken here at Netflix, which is for the studio space. We are a culture of microservices, so different facets of the business domain are owned by different teams that run their services. Those individual services are federated into a large conceptual graph that the user interface and other systems can call into, that then distributes the execution to the underlying service. So my work needed to expose itself as GraphQL in order to participate in this. Another GraphQL feature is subscriptions, which is a way for a GraphQL server to send out a event stream of data. The event stream is whatever the developer decides it is, but this is a mechanism for real-time changes out of a system. And I wanted to have the system be real-time by default and encourage everything else that was built around it to do that. It's 2021. It's entirely feasible. It's just not something that has been done. As mentioned, a lot of these primitives now exist that have been built for the changing app landscape. It is time to bring those into the business application world. And then there were 4 principles that I was thinking about the system itself. The system should never forget anything. The data is the lifeblood of an application. And the never forget phrasing actually goes back to there's an old brand of floppy disks from the 80s from Elephant Memory Systems that had an elephant face on it, and it said never forget. And that's always struck with me. Like, there's no reason to pre-aggregate or throw data away, especially now when storage is almost free. It is extremely cheap. All of the architectural practices for why we would have overwritten something in place because we didn't have the means to store it are now gone. So there's no reason not to keep everything. Event driven is going back to the reactive principles. By keeping everything as events, I can kind of steer things in the system easier. Things are going to be real time by default, and I can kind of I can keep track of what's going on. I wanted to have read and write separation. I wanted to have separate paths for read and write because I wanted this to be a dimension that the system could change in. It may be that the system is going to grow in ways that I haven't thought of. And if there's a coupling of both the read and write paths, then that is a limitation on what my future evolution of the system could be. So even if the everything is ultimately co-located inside of the same process, by having this logical separation between reads and writes, it then becomes easier if I wanted to potentially do a physical separation or add in additional layers on the read side for caching or something else, and kind of keeping them as two separate things. I also wanted to enable partial availability. I wanted to have conceptual bulkheads inside of the system that would allow portions of the system to fail, but not the entire system to fail. And this, my thinking around here is this would be valuable whenever the inevitable incident occurs. By being able to isolate the scope of a failure, the operators of the system know that they only need to look at a certain portion of it when trying to remediate and kind of reducing the scope that they have to think about. So on remembering, as I said, storage is now cheap. As developers, it is a best practice to record all of the changes to our code. So why don't we treat our data the same way? And from a business perspective, a common question I've seen from users is asking, well, why does the system have this value? And unless the system has done something to be able to store that information and answer it, you're kind of guessing to a degree as to what that answer is. And especially if you have ever worked in the financial domain, users really want to know, if you see a number on the screen, what are the numbers behind that calculation? And if you've only stored the result of the calculation, how do you then answer that question? So it can be very important for the business to understand why things came to be. And how is this generally done? So if you have an older system that had this requirement, they'll add a history table and will kind of record changes off in that history table. And it works, but there's a big catch here, is that you're always unifying your database schema across time. Because if you have a table for customers and then you have another table that is the customer history, and every time you make a change in the customer table, you write the old row into the history table. What do you do when you do schema changes for the customer table? You have to do the same schema changes on the history table. If you delete a column on the customer table, you don't want to delete it from the history table. The schemas are going to start to deviate. And again, if you want to think about foreign key constraints and other database constructs, this becomes very messy. And the way I think about it is you're almost really unifying your schema across time by using this approach, which is not something that you want to do. And this also misses a more fundamental thing, is you've lost what really happened. You don't know why the change was made because you're only able to inspect the before and the after of the data itself. So for a change that affected only a single row in the database, it is more straightforward to look at that and kind of tease out what it could have been. But if you have a more complex change that affects multiple rows in the database, the set of things that could have occurred to generate that becomes more complex, and you end up doing pattern matching in your head to try to infer what actually happened. And the answer to that is storing the change, which is the basis behind event sourcing. By storing the change, every change is an event, and events again are messages to be message driven. And we start to use accounting principles of, we're just going to build a ledger, a log of all the changes inside of the system. And we use that as our primitive for storing the data, and we derive everything else from this. And this is not new. Banks do this. They record the individual transactions, and that's the fundamental primitive that is used. When you then want to be able to see the data, obviously looking at a list of changes doesn't work. We want to materialize those changes into a specific schema that is used. When you look at your bank account, you see your bank transactions, and your balance is a materialization of that. And this sequence is then ordered. We can also start to basically number all the individual events as they occurred, 1, 2, 3, 4, 5, and we can start to use that to keep track of what each one of these changes is. For folks that are used to a CRUD API, when talking to them about bringing them into this fold, go to the realization that, well, your CRUD API is really just 3 events: create, update, and delete. And if you want to start your system that way, if you have an existing system that you want to bring in this direction, that's a fair way to start. You can start with those 3 events and then get more fine-grained as you go on into the future. Because with the events, you can start to add new events to capture new things as time changes. You aren't stuck with whatever schema you had when you started out. And I just want to be very clear, this is not novel. Nothing that I'm saying here is novel information. I've been very much synthesizing existing ideas, but I feel that the practicality and the applicability of all of this is kind of coming to the forefront now. Both from, there's these new capabilities in applications themselves. Storage is now cheap. It is completely feasible to actually store all these changes. We're starting to deploy to these more virtualized environments in the cloud. Being message driven and keeping things as events becomes a very powerful way of building systems. So in thinking about starting to decompose how we get there, an event is what has happened. And GraphQL, when it talks about its primitives, it talks about mutations being the way that changes are made. And a mutation is very much a desire to have something happen. And this is then what leads into CQRS, because a desire to make a change is a command. And the commands and events are the 2 sides of the coin relative to state. A command is a expression of a state change that we want to have occur, but that state change may or may not happen according to the business rules. The business has rules about what the data is, and just because you want to change it in a certain way doesn't mean that you'll be allowed to do that. As I said, the mutations are related to GraphQL, and GraphQL is then also extremely CQRS friendly. GraphQL, when you think about GraphQL, it very much encourages schema first. So you're building out that read model according to what the consumers are needed. And when I work with my counterparts for this, I very much talk with the UI designers and the UX and product managers to figure out what their implied model is. Whenever somebody is building a user interface, there is a manipulation of a model that is in their head as they are putting things together. And encoding that model into the GraphQL model as much as possible is absolutely ideal, because you're eliminating the impedance mismatch between what the system presents and how it appears to the user. GraphQL has a very expressive type system. You can create, you have types, they can implement interfaces, you can create union types. And all of this is very useful, but it's only for the read side. The write side, those are considered output types. On the input side, you have input types, and input types are extremely restrictive. Input types can reference other input types, and you can reuse the what they call scalars, like if a string, number, the different types of primitives and enumerations, and that's it. So anybody that approaches GraphQL from a very CRUD system background that thinks, oh, well, I have my, here's my entity model, I'm going to read that entity model, and the write API writes that same model, is immediately flummoxed to a degree, because they are faced with this duplication of, I now need to duplicate my model in two different places because GraphQL itself doesn't let you reuse what's going on. And I think of this as a steering mechanism from GraphQL itself to say, hey, these two things are actually separate. And the GraphQL community plays into this where they prefer specific mutations over general mutations. So not doing the CRUD approach of here's a big blob of data, just go ahead and store it. Very much, I want to approve an invoice. So I'm going to create a approve invoice mutation, not having a save invoice that happens to have approve set to true and backing that information out. And this makes there be a lot of symmetry between GraphQL, the way GraphQL wants you to structure mutations, and commands in the CQRS sense, because those commands are now these fine-grained commands that say, do this specific thing, that then let us then have events that say, well, this specific thing actually happened. So we're then starting to capture the intent that is going on behind the system rather than just the data itself. Thinking about business rules. When talking to folks about, thinking about their system in this way, I categorize business rules into three broad buckets. The first one is our invariance. So the data at rest must always meet these requirements. A customer must have a name. So if you're creating a new customer, you absolutely have to provide a name. And these are the constraints for data at rest. If anything that is a required field, maybe numbers, certain numbers that can't be negative. These are all things that happen for data at rest. Side effects are kind of the business process aspects. After you've satisfied that first bucket, we've created a new customer. We now want to send them a welcome email. So while that is a business rule, it is separate in the fact that the data itself can exist separate from that rule happening. And decoupling those two in both time and space within your code helps separate out those concerns from the system. And the last one, as we like to think of, is transformations of the data, usually for display. So if I receive a financial transaction, somebody makes me a payment and they paid me in euros, but I want to see that data in US dollars. I need an exchange rate for that, but that converted value is not something that needs to be part of my data at rest. That is a derivable value that can be done at view time, essentially. And the reason we don't need to have this be part of the data at rest is because as long as we know the provenance of those two events, we can always reconstruct what has happened. So in a domain-driven sense, this might be combining different aggregates inside of a view where each one of those aggregates is its own little domain. And again, while we are generating new data, the transformation is a non-destructive transformation, and the history for how we arrived at the value is stored by both the input values to the transformation and then the transformation code itself. So as long as you have all of those data points, you're able to reconstruct what had actually occurred. So commands. So a CQRS command from a GraphQL perspective is a mutation, and we're going to use those commands to generate events. And in this little bubble, we need to know that the first category of business rules is satisfied, which is, are we keeping our invariance intact? And in order to do this, we need to know what is the current state of the world. So if we are keeping all of our changes as events, we need to reuse, we can take our event log, our ledger, and we can materialize some amount of state only as necessary to enforce these rules. Because if you have a rule that says, two customers can't share a tax ID, And then you also have another field that is the, the last notes of when that customer had interacted with you. Those notes don't matter for business rules. That's important data within the system, but in terms of keeping the invariance intact, it doesn't really matter. So you can essentially be selective when going through the event log and pulling out the data that's necessary to keep your invariance intact while leaving aside all of the other data that is important data for the overall operation of the system, but not for the enforcement of the invariance. And this kind of then gives us towards a core processing loop that can be the heart of the system. We can start with the event log, which, in day one is empty, but we have an event log which has some set of events within the system. We will materialize those events into some amount of state that is necessary to enforce that first category of business rules. We will take that command, we will look at the state, and we'll determine the set of events that command now implies. We can then update that state that we have with those new commands, and then basically, continually run this. And in our system, we're calling this the command processor because it is processing the commands. And in our case, and in most cases, this is very well suited for a actor model because you have a conceptual single-threaded execution that is going on here. You can read commands from a queue, and you can write the disposition of those commands back to a queue. So there's a certain amount of location transparency that you get as part of this. Depending upon the scope of your system, this is also a place where you can now start to get some amount of elasticity in the overall architecture. Because depending upon your domain, it might be very feasible to partition your overall state space because you may have business rules that are conceptually scoped into certain slices. If this was a system that was keeping track of customers might have things that are customer specific, but some rules, it depends upon what rules you have that are cross-cutting. In the example that I gave where you have the customer tax ID, you do need to keep all the customers together because the invariant about the tax ID says that this is something that is true across all customers. But if you didn't have that requirement, you could essentially partition your space by customer and run those separately. Another thing that I like here is that the command and state to events is a pure function, which makes it extremely amenable to testing, and especially property-based testing, where we can start to now generate commands that match, just generate an arbitrary command, apply that to our state, and we can assert that we know what the outcome should be. And from a business system, this then can give us a very high degree of confidence that our rules are intact and operating as expected. Obviously, if we have this set of events, that doesn't provide the read API. So we need to do something for that. And that is the idea of materializing a view. So if our GraphQL schema defines our view, we can materialize the events from our event log in the exact way to match that schema. The GraphQL schema is authoritative for what we want the view to be. And one nice thing that this type of architecture gives you is you can always materialize that event log in multiple different ways if you have multiple schema requirements. If you can always stand up a new schema and the old schema and be materializing both of those at the same time. GraphQL subscriptions will allow us to be message driven all the way to callers. When a mutation comes in and we generate an event or we generate a command, the command turns into events, those events get materialized into the view. We now know exactly when the view has updated, and we also now have the appropriate trigger to be message driven back to the caller itself. There is a change here that I have deviated from the general GraphQL recommendation, which is often to have a mutation return some sort of description about what its result was. And the catch with that is it feeds back into that old REST style pattern of I'm going to make a change and I'm going to immediately see the result of my change back. And this is not in service of steering UI developers towards making real-time UIs. And that was one of the things I wanted to do. So if we have a query that is get me a customer, there's also a matching subscription for given this customer, stream out changes stream out all changes to that customer. So as the customer changes, you get repeated every time the subscription ticks, you get the new state of the world for that customer. When a mutation happens, the result of the mutation is not here's your updated customer. It is on the customer subscription. You now have a sequence number that says you can see your change at revision X. So I'm steering the UI to use the subscription by default, because if the user might have any possibility of mutating the data, they're going to want to subscribe to the subscription. But now, because you subscribe to the subscription, your page is now real-time by default. So I'm encouraging the system towards being real-time with this mechanism. Yes, as I was just describing, we return this sequence number. The mutation says you can now see your change as of X. We also need to indicate to the user whether or not something failed. So in GraphQL, we are able to use a union type that describes, is it a success or is it a failure, which also lets us very richly describe failures to users, where we can now describe our failure modes inside of the type system itself. Internally, we have this internal flow now where a mutation generates a command. We take that command and we put it on a queue. We wait for the command to be processed. So essentially, there's one queue for commands and another queue that is coming back that is the disposition of processing that command, and that is what gets returned back to the user. Notably, we are not waiting for the view to be materialized before returning the mutation result. The mutation result means that we have actually made the change, but it doesn't indicate whether or not the change is visible yet. And this is because we're now partially available. The first flow, this entire flow is message driven inside, which is kind of achieving, the first two of those, two of my principles, where we have now done read and write separation, and the system is now partially available. Because the reading is separate from that writing the command, the system can be offline for writes, but the users can still read data from the system. And this helps reduce the blast radius of an error, because if there is a, some sort of, maybe there's a problem with the database, it goes into read-only mode, or, any number of weird things that can happen. We are able to be partially available. And for a business application, I then find this valuable because you're able to provide some value to the business by being partially there, rather than this all or nothing that is commonly seen. And we now have our data provenance has been handled. All changes lead back to a command, and we have the freedom to materialize as much history as needed. Depending upon what the business requirements are, we can always adjust that materialization because we haven't thrown any data away. We're capturing everything upfront at the time that it happened, and we can always show more as needed. This also plays very nicely to observability and tracking what's going on inside the system. By having, you start with a incoming mutation, which is a HTTP request. That then message is essentially transformed to different types of messages inside of the system itself. And this lends itself very clearly to a trace model where we can basically spit off a span for each step in our processing and reconstruct that graph of what the system was doing inside of itself. And we can then also return this same trace to the caller that they can then, if they have more things that they're doing, continue to add to this larger distributed trace to see what the overall system is behaving. I found that the GraphQL API, when designed this way, is also very amenable to property-based testing. And we mainly do this for the happy path. Each mutation is making a very specific change. We are then able to generate a random chain of mutations for changing the data in the system. Verify that the mutations are, one, successful. Two, after each mutation happened, the view materialized itself to show what we needed to see, and that the subscriptions are taken properly. So this gives us a lot of confidence that the system is behaving as intended and letting us be able to deploy our changes without worry. And how do we put all this together? And this is where the complementary or the talk that's going on at the same time is very relevant. Where this has been conceptual patterns so far, because I wanted to illustrate the way that we thought about the problem without getting into the details of the technologies, because the technology choices that I made may not necessarily be the technology choices that you make given your operating environment. The primitives that we needed to have some queues for command submission and mutation results. We need some sort of login ledger for long-term event storage. We need some place to keep the materialized view. We need a pub subsystem to drive the subscriptions, and we need a distributed locking system to allow us to have multiple nodes of the system active at one time. As I said, if we have that command processor that is processing the commands, we only want to have one of those, even if we have multiple nodes active in the system. So for us, it made the most sense to satisfy all of this with Postgres, given our operating environment and the need for us to running a new data store is a tricky proposition because we take on all of the operational overhead. So we were able to solve everything with one box. This was very attractive for us. Distributed locking is built into Postgres with its advisory lock function. PubSub is also built in with its listen notify mechanism. A ledger is a very simple immutable table. We can create the view is a relational schema. However, we also engage in logical separation of everything by utilizing Postgres's schemas. So we have a schema for the commands, we have a schema for the events, and we also have schema for whatever the view is. We can also bump the query schema. So as we if we change the GraphQL schema and thus need to rematerialize the view in order to match that, we can create a new schema within the database and rematerialize all of the events into that in order to match whatever the new desired view schema is. Internally, we've wired everything using reactive streams because that lets us have the messaging paradigm of each one of these events is represented by a discrete message that is passed through. And we're actually able to be reactive, from the edge of our service all the way through to the database. We are built on top of Spring Boot, which is in our Netflix parlance, our paved pathway of building systems. And that comes with Project Reactor, which is a reactive streams implementation. And there's also a database API called RGDBC that lets us think in that way all the way through to the database interactions. In the GraphQL API, we're using the GraphQL Java implementation. We have our There's an additional open source framework we have called the DGS framework on top of that that provides some additional conveniences. It is already, it again plays nicely into this because it is future based internally. And that lets us bridge that asynchronousness into the reactive streams implementation we have. Everything is traced using the Zipkin model, using the Brave API. So as requests flow through, we're able to see what is happening. And we're using the excellent JQuick library for building property-based tests. It has a mechanism where you can essentially it will build that chain of actions, and we use that to drive the GraphQL API within our test to understand how the system is behaving. So again, one of the things that we're doing here at Netflix is we have a single federated graph. So the service that I have is part of a constellation of other services that make up the overall composed system that the business is using. There is a dedicated front end to my system that is able to uses my mutations and changes the data that we own. But the read model is available to everybody. So we're using the Apollo's federation model, which describes how to have multiple GraphQL services interrelate. So you can have one service that defines a type, and then a second service can add new fields to that type. There is then a gateway layer that understands which service has which fields and performs a distributed query execution. And we're then using this model to internally evangelize CQRS and event sourcing to other teams to say, this is a different way that you can think about building your service that is compatible with the way that we want services to appear, but it also unlocks some of these additional capabilities. Users, as I said, users are wanting to have these real-time interfaces, and teams are struggling in how to bolt that on top of their existing architectures. So we're kind of trying to offer our core to other teams to give them here's a higher level starting point for you to start to build your systems in this way. So in summary, I've been trying to lay out a path towards building business applications in an event-sourced way. It's, I've been having a lot of conversations with folks at work and elsewhere in terms of kind of broadly, how do we shift the mindset towards this is not only a way to do something, but a way that I've found to be more sustainable and maintainable over time. You are making looser couplings between things, and the system is able to evolve in a very desirable way. And I hope that this is inspiration for you to take back to your teams and your work, and how to essentially spread the good word about event sourcing, CQRS. And if folks want to put a GraphQL API on top, you can absolutely do that. And it really plays to the strengths of what event sourcing and CQRS can provide. So with that, I say thank you, and I hope this has been interesting for you.